So none of that got on record. That was the whole purpose of waiting, so I could get it on there. But didn't make it. All right. Any questions on anything we've done up till now? And there was a question about the quiz. The quiz I gave you last time just because we were almost through with 1.6, but not quite. When we finish 1.6 today, that's when the clock begins, and you have 1 week to turn it in. Though you can have more time if you need it, but try to get it in within a week. Any questions? Did everybody get the quiz last time? No. Okay. Some did not. Okay. Let me find the quiz, and then I may even give you a copy. Okay. All right. Ali? Is it Cameron? Okay. Okay. Here's the copy. You need that one? Anyone else need a copy of the quiz? Okay. And again, it's not due until a week from today, but you can turn it in early if you finish it, and if you need more time, you can have more time as well. All right, let me go and close this door so I don't think that guy moved just because I was so loud. But, anyway. All right, no questions on anything we've done so far. Okay, where we pick up today is step and piecewise defined functions. Now, I think we did this earlier when we were evaluating functions. We talked about piecewise defined functions. Now we're going to look at how some of the standard kind of piecewise defined functions look. Functions whose graphs resemble a set of stair steps are known as step functions. Very creative in their title there. The most famous, I'm not sure I realized it was all that famous, of these step functions is the greatest integer function, which has a sort of unusual function notation. It's a double bar, almost like absolute value, but it has nothing to do with absolute value, a double bar around the variable or around the expression. And here's how that is defined. F of x is the greatest integer less than or equal to x. F of x is the greatest integer function. That's what the symbol stands for. The greatest integer less than or equal to whatever's inside the grouping symbol there. Okay? Now, here's just a few things. What would you guess the greatest integer in -1 would be? -1. It's equal to -1, so that would be it. How about the greatest integer in -1/2? Say again? It's not an integer. Greatest integer. Less than or equal to -1/2. Say again? -1 again. You're absolutely right. Now here's what you do. Picture the number line. Okay? And 0's here. -1 there. -1/2 is here. The greatest integer less than or equal to. Find where you are on the number line, look to your left, the next integer you see, unless you're sitting on an integer like you were here, that's the greatest integer in greatest integer function. Okay, that would be the output. Okay. Now, there are some more of those. Let's see if, yeah, here they go. Greatest integer in 1/10. Is it less than or equal to 1/10?
It's 0.
Say again?
0.
No, it would be, find 1/10, look to the left, what's the next integer you see? 0. Oh, you said 0. Okay, I'm sorry. I thought you said 1. Okay. My hearing's not good. Okay. I got 1.5. Greatest integer in 1.5. 1. Excellent. Greatest integer in 1.9. 1. Absolutely. Greatest integer function has these characteristics. Now, these are I don't like this setup, but I'm stuck with it. Okay? First, the domain is what? What can you put in a greatest integer function? All real numbers. Yeah, all real numbers. What's the range? Integers. Positive or negative integers, but you can't have anything in between. Okay, the integers. Okay? And sure enough, it looks like a stair step, doesn't it? Okay? Going up the thing here. Now notice, greatest integer in -4 is -4. And then anything here that when you look to the left and you see -4 as your first integer, that would be -4 as well. But not -3, because at -3 you're sitting on an integer, so then you jump up to here. Then you go across here, jump up to there. Okay, that's how the greatest integer function works. Now, this is just one example of a stepwise type function. Okay, let's look at a few other characteristics. We already said the range is all integers. The graph has an intercept at 0, 0, and the y-intercept, of course, excuse me. Thank you. Y'all awake yet? Okay, good. There is only one y-intercept. That open circle there is not an intercept, not there, up to there but not included there, but at 0, 0. But look at the x-intercepts. Every value between 0, including 0, and 1, but not including 1. This is a bracket, that's a parentheses, okay? So that's your x-intercepts. An infinite number of them, by the way, okay? It's constant between every pair of points, but then jumps vertically 1 unit at each integer. So you can't really call it an increasing function, though overall it increases. It's constant in little spurts, but then increases with jumps. So you don't really call it increasing, decreasing, or constant, unless you're specifying where you are. Okay, how about symmetry? Does it have any symmetry? No. It's not symmetric about the y-axis, not symmetric about the origin. It comes closer to being symmetric about the origin, but still isn't. Okay, so it's not symmetric. So is it even or odd or? Say again? Neither. Okay. All right. Now, here's example 2. Evaluate the function when x is equal to -1. Okay, and then the other two. So let me get my pen set up. All right. So f of -1 would be the greatest integer in -1 plus 1. What's the greatest integer in -1? Help me. Say again? Not positive, -1. Okay? The greatest integer less than or equal to -1. And it is -1, because that's what its value is. So this is -1 plus 1, and what's that equal to? 0. All right, good deal. Okay, do you see that? The greatest integer in -1 less than or equal to -1. So if you were doing a number line here, okay, there's 0, 1, 2, 3, and -1, -2, -3. Okay, and if you're at -1, you look for the greatest integer less than or equal to -1. Well, -1 is equal to -1, so that's the greatest integer in it. Okay, you would go down here to -1 and put the dot here, but I didn't do it. I just did it one-dimensional. Say if it was -1.5, the greatest integer in that look to the left, it's still negative 1. If it's negative 0.5, look to the left, that would be 0. You always look to the left and find the next integer. Okay. Now, okay, let's do 2. F of 2 would then be the greatest integer in 2 plus 1. What's the greatest integer in 2? Less than or equal to 2. 2. Okay. Plus 1 is 3. All right. High level math today. How about, yuck. So aggravating. All right. F of 3/2. That's the greatest integer in 3/2. You put the x in everywhere you see it. 3/2 everywhere you see an x plus 1. And what's the greatest integer in 3/2? 1. Excellent. Yeah. Look to the left and you see a 1 plus 1 is 2. High level math today. Okay. Good deal. Now, let me give you a little hint. I hope that'll make this make sort of sense as long as you apply it correctly. If you wrote that 3/2 as a mixed number, what would it be? 1.5. If you wrote it as a decimal, what would it be? 1.5. So any positive number, if it's something in between, write it as a mixed number or mixed decimal, throw away the fraction or the decimal. The greatest integer will be what shows up there. And even if you don't have 1, 2, throw it away, it's going to be what shows up there. Okay. Now when you do negative numbers, you can't do that anymore. Okay? Negative 1.5, what's the greatest integer in that? Negative 2. Okay, the greatest integer in that would be negative 2. You can't throw away the decimal there. You always look to the left, and left of negative 1.5. See, negative 1 is right of 1.5. Negative 2 is left. You look that way and you see negative 2. But for the positive numbers, just throw away the fraction. Throw away the decimal. That's the greatest integer. Okay? Make sense? Maybe a little bit, somewhat. Let's see how they do it. I think they've already started. Let me clear my ink. Okay? For x equal negative 1, just like we said, the greatest integer less than or equal to negative 1 is negative 1 because it's equal to it. Okay? So the f of negative 1 would be the greatest integer in negative 1 plus 1, which would be negative 1, because that's the greatest integer in negative 1, plus 1 would be 0. Okay, just like we said. Then when we do 2, the greatest integer in 2 is 2, so it would be 2 plus 1 is 3. And for 3/2, the greatest integer less than or equal to 3/2 is 1. If you get the 3/2 on the number line, look to the left, the next integer you see is 1. So the greatest integer in 3/2 is 1, and 1 plus 1 is, of course, 2. Okay. Now, that one looks a lot like what we just had before. Let's scoot back. Ah, there it is. There was greatest integer function. That's all it is. When you add a 1 to it, when you add a 1 to it, you move everything up 1. Remember before, the one that we had before, this line was down here, this one was down there. That one, everything was jumped up by 1 because you added 1 to the greatest integer function. Everything was lifted 1 unit. Everything. Now that's one step piecewise defined function. They say it's the most famous one, okay? Honored to be in its presence. By the way, there's a checkpoint here. Please do the checkpoint as soon as you can after class, okay? Let me give you some examples. This isn't the only one, and this one, frankly, I've very seldom used. There are applications for it, But have any of you ever mailed a letter? I know that's sort of old technology. Oh, yes, you have, okay. Now, most letters will go for a fixed rate. I don't even know what it is now. We use the forever stamp, so I never know what its rate is anymore. 52 cents or 48 cents. I don't know what it is, okay. But if you're more than an ounce, there's a different rate. And that's good for that ounce, from 1 ounce to 2 ounces. But then, if you have another ounce, it goes up again. Again, a piecewise defined function, I think just as famous as this one, okay? It just starts at a different place. At 0, well, okay. The one with that one, you don't have a letter that weighs 0 ounces. So let's just imagine this is 52 cents. I don't know what it is. 0 wouldn't have it. It would be the open circle there. And for the first ounce, it would all be 52 cents or whatever it is. Then you have a closed circle there because it's right on an ounce there. And then you jump here, and then it's not an even. That first step is a shallower step than from 0. But then from there on, I think it adds the same amount every time. Some of the old cell phone plans, for so many minutes, you got it at a certain rate. Any minutes over that, then it goes up an increment. Those are all piecewise defined functions, right? You use them all the time and probably don't even realize it, okay? Step functions. Now, they skip completely example 3, which is really a shame because that is a little more involved function than the others, but you can go to larsonprecalculus.com with no access code, absolutely free. Just go to that for an interactive version of this type of example. So you might want to do that. But here is another piecewise defined function, not a step function. It says sketch the graph of this one. F of x is equal to, and it's a piecewise defined function, and we did these before when we were evaluating them. Now we're graphing them. 2x plus 3, and that's good anytime x is less than or equal to 1, okay? And it's minus x plus 4, and that's anytime x is greater than 1. Okay, it says to graph that. All right. I'm not going to need all those x's, but I'll put them on here. I'm probably going to need some more y's. Not a very pretty graph here. Don't act like you're surprised. Or not. Okay. Now, how would we go about graphing that? You tell me. How would you graph that piecewise defined function? I can think of a couple ways to proceed. You tell me how you would proceed. Yes? Yes! Plug them in, just like Glade, okay? Now, pick me a number. 5. Okay, she chose 5. Okay, you got to first figure out, where are you, Waldo? Okay? And where are you in this? Say again? It's greater than 1, so you're on the lower part. So when you got x equal 5, 1, 2, 3, 4, 5, right there, you do minus 5 plus 4 is minus 1, right? All right, good deal. There's a point. Everybody see it? Give me another x. I feel like a cheerleader here. Give me an x. Okay. Never mind. Okay. Say again? 0. Okay. Where are we, Waldo? Say again? The upper one, because 0 is less than 1. Okay? So you plug a 0 in there, and what do you have? 3. So there we have another point. Okay? Does anyone have any suggestions how to go from here, or just keep plugging points? You tell me. We can keep plugging and chugging. Or we can maybe do it a little bit. Say again? Slope, excellent. Both of these are linear functions. So this one has a slope of 2, positive 2, and we just found the y-intercept of 3 right there. But it only goes one more space because it's only good up until, whoops, I put it in the wrong place, up until there. It goes up by 2 to 1, but it stops right there because of the equal sign. But then going the other way, it's down to left 1, down to left 1. My graph is not very good. Down to left 1, and so on. So there, something like that is the linear function of the first part. That's the top part. Okay? Stops at 1, though. Okay? How about the second part? Slope of negative 1. Okay? That's going down 1, right 1, every time you go to the right 1. But it's going up 1, left 1 for every one that you go up. Okay, now here's where most people will make a mistake. They'll stop right there because they say 2 is greater than 1, but 1 wouldn't count. But you notice here, it's everything greater than 1, not just the next integer greater than 1. So go on and plug a 1 in there, even in that bottom one. And what value would you have? 3. Now, I must have done something wrong here.
I thought 3 and 4 were points in the graph.
What's that?
3 and 4, I thought it was supposed to be points in the graph.
Oh, you know, I see what I've done wrong. Yeah. I went up too high. Okay. Okay. My graph isn't very even. This will be at 1. This will be at 2. So this would be at 3, but it's not at 3, but it's an open circle there, right up until 1, and then it goes down like this, slope of negative 1. Okay? There's where you'll tend to make your error, because the top one does include 1, and you evaluate it there. The bottom one doesn't include 1, but still evaluate it there, but put an open circle, because it's not really there, but it goes right up to there. Okay? So you see, this is how it works. Slope of 2, positive 2, with a y-intercept of 3, and this is the slope of negative 1, and it doesn't ever reach its y-intercept, but it would have been a 4 here if you had it. But it stops at 1 and doesn't even quite get to 1. So always put the open circle at the end where there is no equal sign. Put a closed circle where there is an equal sign. Does that make sense? All right, good deal. Any questions? Please ask if you have questions. Okay? Said this in my class yesterday. May have said it already in this class. But I said, when I was in the Navy, and the guy started laughing over here, he's stationed at Fort Benning, so he's in the Army, and he was making fun constantly. I've never, but anyway, he's flailing, but never mind. Just kidding. All right, just kidding. Okay, but anyway, they had a saying at every Navy school I ever went to, so it must have been something they taught all their instructors. They said there is no such thing as a stupid question, except for one. There is one stupid question. That's one that you have that you don't ask. That's it, exactly. Were you in the military? Okay, they use the same thing there too. So please, if you have a question, it can't be stupid if you ask it. It is stupid if you don't ask it. And here's my take on that saying, because if you have that question, there's a really good chance that at least half the class would have the same question if they thought enough to do it, or they already have it, but they're scared to say it. So please, ask questions if you got it. Any questions on that? That's example 3. Now we get, finally, if there are no questions, to the parent functions. Okay? Sort of like the parent trap, only different. Okay. We talked about these, and these are 8 graphs that show basically what these commonly used functions in algebra look like. Okay, the first of these is the constant function. Whatever your f is constant throughout. Okay? It could be a negative number, it could be a positive number, it could be a decimal fraction. Irrational, okay? Any number, but it's always constant. The domain is always all real numbers, okay? And the range is help me somebody. The value C. That's the only value y can ever take on. Is C. It's constant. It never changes. Okay? X-intercept. Trick question. X-intercept.
For A?
Say again?
Are you talking about for A?
Yeah, for A.
There's not.
There is not one. Unless, of course, that constant was 0, and then all of them would be x-intercepts. What's your y-intercept? C. 0, C. Exactly. Always give your intercepts as ordered pairs. Okay? Is it symmetric about the... Does it have any symmetry? About the y-axis, exactly. So therefore, it's what kind of function? Okay? Or? Is what? Even function, absolutely. An even function because it reflects across the y-axis. All right, here's the identity function. That is whatever your x is, your y is. 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2. It's the identity function. Okay? What's its domain? All real numbers. Its range? All real numbers. Symmetry. Does it have any? About the origin. So what kind of function is it? Odd. It's an odd old function. Okay? What about x-intercept? Second? The origin, 0, 0. How about the y-intercept? The origin, 0, 0. Absolutely. Okay? This is the absolute value function. We didn't do a whole lot with that. The absolute value function is always with these V-shaped looking things. They could be, depending on what your signs and stuff are, they could be offset or upside down or something, but they always look like a V. But the parent function, absolute value function, wherever x is, f of x is always positive, the positive value of that. So if x is positive, your y is positive, just like your identity function, okay? But if x is negative, this flips over and becomes positive because the absolute value means positive value, okay? So it goes up like this, minus 1, 1, minus 2, 2, okay? That's the absolute value function. Even or odd? Say again? Even or odd? Help me, somebody. I'm drowning. Huh? Even, absolutely. Symmetric about what? The y-axis. Excellent. Y-intercept. Yeah, the origin, 0, 0. X-intercept. The origin, 0, 0. Is it, what's its domain? All real numbers. No, this one, all real numbers. Okay, what's its range? That's what you're answering. All positive numbers or non-negative numbers, because 0 is not positive or negative. But yeah, all non-negative numbers from 0 to infinity, and that's your bracket there. Okay. This is the square root function. What's its domain? Say again? All non-negative numbers. You can't take the square root of a negative number. So it's all non-negative numbers from 0 to positive infinity. 0 has a bracket by it. Okay? Range. Same thing. 0 to positive infinity. Because it's a principal square root, meaning positive. Symmetry. No, it doesn't have symmetry. Even or odd. Neither. Okay, that's one of your neither functions. Okay? X-intercept. Help me. Easy. X-intercept. 0, 0. Y-intercept. 0, 0. Very good. Okay. The next four, earlier they called it the squaring function. Now they're giving it the quadratic function. Squaring is actually, I think, a little more precise because any function that looks like this can be quadratic, maximum exponent of 2. This one is just squaring the number. So I prefer calling it a squaring function. But all other quadratic functions look just like this, only they may be fatter or skinnier. They may be over here, over there. They could be upside down, but they all basically look like that. We'll talk about that in the next section. Okay? What's its domain? Domain. Say again? Domain? Someone started to say something. Domain. Help me. Not that hard. All real numbers. You can choose any number in here and you can square it. Okay? Range. Okay, all non-negative real numbers from 0 up. Yes. Because you square any number, positive or negative, it's always going to be positive. Except 0 and that's 0. Okay? Symmetry. Across the y-axis, so what's this? Even or oddness? It's even. Okay? Cubic function. Okay? And there are many other cubic functions now, but if we call this the squaring function, this should be the cubing function, but they just call it the parent function for the cubic functions. Is f of x equal x cubed. Domain. All real numbers. You know, I've been forgetting one thing. Let's go back to this one. Increasing, decreasing. Where? No, this one. Quadratic function.
It's decreasing.
Decreasing from
negative infinity
to 0 and increasing from 0 to positive infinity. And when you talk about increasing, decreasing, always use parentheses. You don't need to use brackets or anything for that. So, cubic function. Increasing, decreasing. A little louder. It's what? Increasing everywhere. Even here where it looks like it might be getting a little flat, it still is ever so slightly increasing. Just very, very slowly. Okay? Symmetry. The origin. So it's even or oddness. Odd. Domain. All real numbers. Range. All real numbers. Very good. All right. This is the reciprocal function. F of x is 1 over x. Pretty good name for it. What's its domain? Exciting stuff, no? Okay. Domain. All real numbers except 0. You can never divide by 0, can you? So it's all real numbers from negative infinity to 0 with a parentheses there, and from 0 with a parentheses there to positive infinity, but not counting 0. Okay? Even or oddness. Or neitherness. What you think? Odd. It is an odd function. Whatever you're doing here, you do the opposite over here. Okay? Range. I'm mixing these up. Crazy. Okay? What's the range? All real numbers except 0. Okay? Because whatever x you put in there, you can make it as big as you want to. The x is big. That makes the f of x small. Makes x very tiny. That makes f of x very huge. Negative, it goes in the opposite direction, but it can never be 0, because the only way it could be 0, the y could be 0, if that numerator could be 0. It can't. It's a 1. It can never be 0. Okay. Increasing, decreasing. decreasing everywhere that is defined, okay? Because it's not defined at 0, you can't tell what it's doing there because it's not even there. But decreasing everywhere else. Decreasing from negative infinity to 0, not counting 0, and decreasing from 0 to positive infinity, but not counting 0. Okay. And then finally, your greatest integer function, which I think the parent function would be stepwise function, but greatest integer function, we just beat that to death. All right. So if you know this. Now, let me give you a few hints here. I said that all quadratic functions do look like this. They may be located in different parts of the plane, but they all basically look like that. Fatter, skinnier, term. The cubic functions can look very different. If you take this middle here, you notice here, it acts like it's going to come up and decline, and that looks like it was doing something else. If you put more terms in here, what you have is one function goes up, another goes down, and it winds up like that. The cubing function itself doesn't have that change of direction. It always is increasing. But most cubic functions will have some portion that's doing the opposite thing from the others. Just to let you know. Okay. So these are your parent functions. Are they apparent to you? Never mind. Okay. That's it for this section. Let's do the vocabulary, top of page 65. Okay? Most of you have books or access to a book? Not? Okay. I'll write them down. Okay? All right. Write the most specific name for the function. What's the most specific name? Greatest integer function. Okay? The what? It is a parent. All these are parent functions. Which one? Identity function. Excellent. How about this one? Reciprocal function. Excellent. Say again? Either the squaring function and the book called it the quadratic function right at the end. Okay? How about this one? The square root function. How about this one? Constant function, exactly. Okay? Absolute value function, very good. Cubic function, excellent. Now that one, to me, is not a parent function, but it is a pretty common one. What is it? Linear function, exactly. A standing for slope, B standing for, say again? B was what? Y-intercept, okay, yeah, I like it, okay. All right, now, number 10, fill in the blank. The constant function and the identity function are two special types of what kind of function? The constant function and the identity function. There's the constant function, there's the identity function. Those are special types of which other kind of function? We have on the board. Think about what the constant function looks like. Think about what the identity function looks like. They're what? Linear. Yeah, they're both linear functions. The constant function is when a is 0, and all you have is f of x is equal to one number. It's b here, it's a c there. I don't know why they use different letters, but it's just there. The identity function is when the b is 0 and the a is 1. Yeah, they're both linear functions. They graph as straight lines. Okay, good deal. All right, homework exercises, either 11 or 13. They're both at calcchat.com. 11's at calcview. And here we have Ryan. Got it. Okay. All right. Anyone else come in since I called roll? Okay. Then any of the odd functions 15 to 25, they're all at Calc Chat. Do either 27 or 29. They're both at, and this is pretty much where we started today. 27, 20, both of them are at Calc Chat, 27's at Calc View. Either 31 or 33, they're both at Calc Chat, 31's at Calc View. Any of the odds 35 to 39, they're all at Calc Chat, 35's at Calc View. Do number 41 is at Calc Chat, and then do any of the odds either 43 or 45. They're both, any of the odds 43 to 47. They're all at Calc Chat. Okay? Then number 49 is a true false. It should be at Calc Chat as well. Any questions? 1.6. Yes. Say again?
You said we got to take home
a quiz, yes.
Yeah, can I get that?
No, you can't. It's too late. No, I'm just kidding. Okay. All right. Anyone else need a quiz? And you need graphic. Oh, you didn't? Huh? Graphic. What's that? You need it, quiz? Oh, you didn't get it last time? Huh? Anyone else need the quiz? All right. They're technically due 1 week from today. You can get them in early if you want. Huh? One more. Jalen, got it. Didn't know who you were behind those foster grants. Okay. Yeah, Jalen. Got it. Anyone else need a quiz? Okay. You need one? I passed it out last time you weren't here. Okay. Do you need graph paper? Okay, let me see. All right. So that's it for 1.6. Yes. Oh, I thought there was something. Question? Okay. Okay. Let's move on to 1.7. Really batting along here fast, aren't we? And this is what I was talking about with at sort of the end there about the parent function, how they can change. What we're going to do now is, I don't know what in the world, oh, I see what that is. Okay. Let's do slideshow from here. Okay. Still doing functions in the graphs, and if you haven't noticed it, folks, this author loves graphing, okay? Just about every quiz and every test will have at least one graph on it. Maybe not everyone, but most of them will, okay? Some of them will have more than one. Now we're going to start transforming those functions. We had the parent functions that all look and act the same most of the time. Now we're going to do some transformations. We'll do vertical shifts and horizontal shifts. We'll reflect graphs, and we'll do some non-rigid transformations, which are either stretches or squishes, or compressions, okay? So there will be non-rigid transformations as well, okay? Ready to go? All right, first we're going to deal with these shifty graphs. Okay, Grafton shifts. Many functions have graphs that are transformations of the parent functions. For example, here's a really simple one. We already saw one in that greatest integer function. We shifted it up one, remember? Here we're going to take a squaring function and shift it up 2. So it's going to take that original squaring function and just raise it 2 units, because what are you adding to here? What is f of x? Y. you're adding to y, so this is a shift upward. Okay, the h of x is taking your f of x and adding 2 to it. So it's going up 2. Say 2, don't say yours. Okay, so up 2. Okay, so this will go up 2. 1, 1 would go up 2 to 1, 3. Negative 1, 1 would go up 2 to plus 3, and so on. Okay, so every value on the parent function, you go up 2, and you get the new function. That's called a vertical shift. You're going up. What if that was a minus sign there? You go down 2. Okay, very good. All right. So, catch this now. Anything you're dealing with the y's, you follow the direction pretty much that it makes sense. Okay? This is what we just said. Another way of looking at that, if alpha of x is your parent function x squared, this is alpha of x plus 2. So basically it's shifting the whole graph up 2 units. But what happens if we move the 2 inside the parentheses and you're subtracting 2 from x? Guess what kind of thing is happening there? Yeah, okay. This is a horizontal shift because you're dealing with the x, which is on the horizontal axis. The y is a vertical, so that's going to be a vertical shift. This is going to be a horizontal shift. But guess what, folks? You go the opposite direction you would think. If you do x minus 2, that's not to the left, that's to the right. Anything dealing with the x seems like it's backwards. Okay? So this is going to the right. And there's a reason for that. Okay? You want to catch it? If that was just the parent function, what would be the origin, the x-intercept? 0, 0, right? Well, where is this one equal to 0? Not at negative 2, but at positive 2. Put a 2 in here. 2 minus 2 is 0. That moves this way. So sure enough, that's a right shift. Okay? Even though it's a minus sign. You always, with the x's, you always go opposite what the sign is. So this is a horizontal shift to the right, 2 units. Okay? Now, any questions on that? Okay? New function, horizontal shift to the right from your parent function. And I bet you some of you are already saying, can you do them both? Sure you can. We may not yet, but you can do them both. In that case, the one we just talked about, you have f of x minus 2, which is a shift to the right of 2 units. So here's a summary of shifts, okay? Horizontal and vertical shifts. Let C be a positive real number, okay? Vertical and horizontal shifts in the graph of y is equal to f of x are represented as follows. Bless you. Okay? A vertical shift C units up is going to be what? If you're taking that parent function f of x, whatever it is, okay, and your vertical shift C units up, what would you do? H of x would be f of x plus C. Exactly. And if you're shifting down, alpha of x minus C. If you're shifting to the right, it would be alpha of x minus C. You're absolutely right. And if you're shifting to the left, it would be x plus C. Okay, alpha of x plus C. Does everybody see that? See, meaning yes. Okay. All right. Any questions on that? Vertical and horizontal shifts. Okay? Some graphs can be obtained from combinations. That's what you were asking before, weren't you? Vertical and horizontal shafts. And we're going to do this in example 1b. Or did we already do 1b? Okay. I think they skipped 1b. Let me just see if they do it. No, they didn't. Okay. Vertical and horizontal shifts generally create what we call a family of functions, each one with the same shape but a different location in the plane. So let's do example 1. here is our parent function. F of x is equal to x cubed. I think I'll go on and graph that one. I'll get my pen back. Okay. Not very even spacing there. Okay. Okay. How do I graph f of x is equal to x cubed? Give me a few points or pointers. F of x equal x cubed. Earth to class, come in please. Okay. Say again? Okay, say it one more time. Yeah, so f of x cubed, that's what I'm graphing now. Give me a point that's on that graph. The origin, 0, 0. Another? Did I hear 1, 1? Say yes, okay. Negative 1 what? Negative 1, negative 1. Okay. 2. Eight, yes. Negative 2. Negative 8, way off scale here, okay? So this one does something like this. That's what your parent function, your f of x equal x cubed. Y'all knew that, okay? Now, says, let's now do, and I need a different color. Someone give me a color.
Purple.
Purple, okay? There's purple. So we'll do G in purple, okay? How could I graph that? I could plot points again, or what else could I do? Your parent function. Go down 1. So this one goes down to here, this one goes down to there, this one goes down to there, this one goes down to there. The one down there we can't even see, so it's like this. Yeah, it's just like it, if I could draw, just like it, but shifted down 1. That's your g of x, okay? Since you already had those points, just take each one of them down 1, down 1, down 1. And you got it not. Okay? How about the B here? We need a different color for it. What color you want? Anybody? Huh? Green? Light or dark?
Dark.
Dark. Okay. I can't hear, so it doesn't matter what you say. Okay. All right. You should have seen me with a group of high school students one time. They were not saying anything. And whatever they say, yeah, and then go home, and they all just burst out laughing because I couldn't hear what they were saying anyway. And we had a good time. Okay, so what are we going to do with H? We're going to do it in green. So what are we going to do with H? Say again? What are we going to do with it? We could start plotting points again, or... Okay, go back to the parent function, always the parent function. And what would we do? Left 2 and up 1. You got it. That was our origin. This one goes left 2 and up 1. This one goes left 2 and up 1. This one goes left 2 and up 1, something about there. This one still won't be visible, so it's like this, okay? Same shape, exactly the same shape, but now we've shifted left 2 and up 1. So sort of our origin is moved over to there, okay? And then everything else goes from there. Does that make sense? Or you could plot points. Pick a point, evaluate it, and stuff like that. That's extra work. And guess what? I'm lazy, okay? I like to do it the easy way, okay? That's what it takes to be a good mathematician. Just a little bit lazy, okay? Always trying to find the easiest way to do a problem. All right. Everybody got it or still writing? Who's still writing? Okay. Done? Okay. All right. Let me erase my scratch here. My beautiful artwork here. I'm sorry, I misstated. Okay. And relative to the graph, and there's the gray is their parent function. Relative to that, we did for the G, shift down 1. Everything went down 1. Every point on there went down 1 and changed the color. Okay, never mind. Okay, that's the black line. Okay. They have theirs a lot flatter than mine was, but you got the general idea. Okay? For the second one, the B one, it's both a horizontal shift to the left. Remember, the plus on the X takes you to the left, and the plus on the 1, the vertical shift takes you up. Okay? And so everything gets shifted left 2, up 1. To say 1, not yours. Okay? Got it. All right. Now, any questions? All right. Let's see what happens next. Okay, everybody got it? Okay. Now, in example 1b that we just had there, you can obtain the same result by doing the vertical shift first and then the horizontal. It doesn't matter the order in which you do your shifts, okay? They'll come out either way. If it precedes the horizontal shift or when the horizontal shift precedes the vertical shift. The order doesn't really matter much here. Now later, some of these they might. And the next thing we're going to do is reflecting graphs. All right. I think we've got a few minutes here. I don't have my clock on. I have my watch, but it's a little fast, so I don't have it on the computer. Another common type of transformation is a reflection. Okay? Now, these reflections are also keep the same shape, but they change the direction. The shifts change the location, but keep the same shape, but the reflection keeps the same shape, but changes its direction. So here is a reflection. If you consider the x-axis to be a mirror, then h of x, which is minus x squared, is going to take f of x, which is x squared, and reflect it across the x-axis. So when you negate the y, okay? Now notice here this is outside the x squared. You do the squaring before you negate, so this is taking the whole function and negating it. 0, negative of 0 is 0, negative of 1 is minus 1, negative of plus 1 is minus 1. So every y value you flipped across the x-axis, you negated it. If you had had some that started down here and went up, these would go up, these would go down, okay? Whatever they are, you negate it. A mirror image or a reflection of the graph, okay? That's when you negate the y value, the function value. That is a reflection across the x-axis, okay? Now, they didn't show you an example of the y, but here's what it will be. The reflections in the coordinate axes are, if your parent function is f of x, y is equal to f of x, then the reflection across the x-axis negate the f of x. Whatever was up here goes down, whatever was down here goes up. Negates it all, okay? But a reflection in the y-axis is if you had a f of x that was, say, doing this, and you negate that, you flip it this way across the y-axis, and then it would be like that. Now, sometimes they look very similar to each other, but you just have to pay attention to what you're negating. If you're negating the y, flipping across the x-axis. If you're negating the x, it reflects across the y-axis. Does that make sense? Okay. Okay. I'm guessing right now we're probably running out of time. Is that right?
Yes, that's right.
Okay, so we don't have time to do example 2. That's where we'll pick up next time. Okay? Let me get something in to mark my place. Let's see if we got enough to do a few homework exercises in this one. You can do either 5 or 7 or both, and they're both at calcchat.com. And you can do some of 9. You can't do them all. I think you can do A and B, D, E, F of 9. Okay? But don't worry about the others. We'll do those later. Okay? And we'll pick up the rest of those later. Mostly 1.6. All right. Any questions? All right. Now, remember, you have your quiz. Try to get it done by next Tuesday. If you get it done beforehand, you can turn it in beforehand. But especially review it, start working on it, make sure you understand what I'm asking, so on Thursday you can ask me questions. Now, the questions may be, I don't understand what this is asking for, or what you mean by this, or could you read this one to me? I can't make out if that's a plus or a minus, something like that. But if the question is, can you work number 7? My answer will be yes, but I'm not going to, because that's a quiz question. What you can ask, that I will always do, is anything from the book. So if you can find a problem similar to it in the text, I'll be glad to work any of those. Okay? If that's what's giving you problems. Good deal. All right.